The floor is yours.
Great. Okay, good morning, everybody. So, as Elaine said, my name is Andrés Martinez, and I will be offering this presentation today towards population level reliability assessment of building structures. I just started the PhD a couple of weeks ago, so this I'll just talk about some initial thoughts that I had during the preparation of the PhD project and some ideas for the future. Well, about the titles, as you can see, we are going to focus on building structures, and the way that we're gonna evaluate these structures is going to be with a reliability framework, so in a probabilistic way, and at population level rather than at individual level. So I'll just start. And the presentation is kind of long, so I think it's maybe better to wait for the questions at the end so that we don't have any issues with time. So this is an outline of what I'm going to talk, very brief. So at the beginning, we're going to motivate why using a reliability approach. And we're going to go, then we're going to explain the ideas to go from individual buildings to populations of buildings. Then we're going to outline some preliminary work that we have done and some challenges that we have identified so far that we will need to tackle, and some conditions at the end. Then just a bit about me before. So I'm a researcher at TNO in the Netherlands. So it's the Netherlands Organization for Applied Scientific Research. That is the name of the institution. So it's a semi-public institution there. We work in different industries, but myself, I'm in the mobility and built environment unit, and specifically in the risk and reliability. I did my bachelor's in Peru in civil engineering a while ago already, and then I went to the Netherlands and did a master in structural engineering at Delft. So as I said, I started a couple of weeks ago here, and well, my interests are in structural reliability, in the usage of Bayesian methods in digital twinning and machine learning. Here are some selected publications. Well, I'll also upload the slides somewhere, so you can take a look there if you want, and if you want to discuss about any of these publications, yeah, I'm more than happy to do it. Okay, so why reliability? So for the life cycle of a building, you usually need to evaluate its structural safety. So you need to answer queries such as, is it feasible to change the occupancy of this building? So you have an office building and you want to transition to residential building. How can you do it? Is it feasible to do it? Or maybe the design lifetime is over. So the 50 years that were specified in the code are already passed. Do we need a retrofit? Or maybe the wind standards have been updated. Are we still compliant? Or even going more towards the insurance industry, well, what should be the insurance premium? So Eurocode approach to do it, for instance, partial factor checks are always possible, but what we argue here is a reliability approach is more convenient for reasons that I will explain. But for those that are not very familiar with reliability analysis, here are some principles about it. So the parameters that influence structural safety, materials, loads are all uncertain. So either because of their inherent randomness or because of our lack of knowledge about them, they are uncertain, and we have to deal with that. So this forces us to approach failure of structures in a probabilistic way. We do this by treating parameters as random variables, and then we define a limit state function. Limit state function separates safe and failed states. And on the right, you see a typical graph that is shown to represent reliability. So on the distribution on the right with an R represents the resistance of your structure, and the one on the left, the load effects of your structure. So failure occurs when the load effect is higher than the resistance, but since these are two random variables, it's not a binary question, but more a probabilistic question. What is the size of the overlap? This is a representation, by the way. The area is not precisely the probability of failure, but it's a way of representing the overlap. So if they are very close to each other, then the overlap will be big, and then the reliability will be low, and the opposite if they are very far apart or they have a low spread. And then I will also be talking today about betas, which are reliability indices. So this is a way of transforming a probability of failure that can be in the range of 10 to the power of -1 to 10 to the power of -6. Then we translate them into more palatable numbers, between 2 and 6, so to speak. So it's this formula on the bottom that is used for that transformation. So we'll be talking a lot about betas today. Okay, but then why not just apply partial factor checks? So one explanation is that partial factors are calibrated across a broad range of cases, so Eurocode partial factors, for instance, and this creates a wide scatter in the reliability. So this is, for instance, a picture of a study by Köhler about calibration of existing semi-probabilistic design codes, and you can see that for different load effects and for different elements or failure modes, structural steel yield or concrete compression, there is quite a lot of spread in the actual reliability indices obtained versus the target of the code, which is the red dotted line, in this case 4.7. You can see that if you apply the exact partial factor by the Eurocode, you end up having very different results. So passing a unity check is not guaranteed adequate safety in either direction. Another reason is that, unlike a unity check, a probability of failure is a consistent and actionable metric. So here, for instance, a capture of the Dutch renovation code for buildings. So here are different consequences class and reference periods, and they tell you that for reconstructions, these are the target reliabilities that you need to achieve. So this is, let's say, more interpretable, and you can check compliance with this code threshold. And even more interesting, a probability of failure is something that can be monetized. So if you have a probability of failure and then you have a consequence of failure, you multiply them and you get a risk cost. And then you can compare this with the cost of making improvements in the buildings. So then you have risk-based optimization. So probability of failure allows us to get this. And finally, and perhaps more interesting, is that extra information can be used for reliability updating via asynchronous. So the information that you have, it can be used to refine the input parameters via the Bayes theorem. And with this, you have a reliability before observing the data and a reliability after observing the data. So it's a very consistent way of incorporating this information. This is, for those that are not familiar, Bayes theorem for continuous variables. So you start with a prior distribution. So you have this theta, which is the parameter of interest. Then you incorporate the data that you have via the likelihood function, and then you get a refinement of this prior in the posterior distribution. And one quick example of what this means for reliability updating, this is a case of proof loading. In proof loading, as you know, you apply a predetermined load, and then you check if the structure survives without damage. If it does, then you see that at least its resistance is as low as the proof load that you applied. So then you can truncate the left tail of that distribution. And you see the baseline reliability on the left, there's like a big overlap. But then once you apply proof load, you do a Bayesian updating on this resistance distribution on the right, and you see that the overlap is much smaller. So this is how effective can be. And following this thread, the building information, buildings have a lot of information that can be used for reliability updating. So on one hand, you have archival information, you have operational load histories, you have the fact that the structure may have survived an extreme event such as an earthquake or a storm. You can have access also to construction and maintenance records, quality control logs, and so on. You also have some observational data available sometimes, remote sensing, visual inspection even, or non-destructive testing. And already going to the more interventionist part, experimental data is also available sometimes. You have the material testing, load testing as the case that I presented before, or even operational model analysis data. So then I wanted to show this example to make things a bit more tangible about the potential of using reliability. This is a timber connection, actually the case that we studied, and it's loaded in tension. It's a steel timber connection with steel dowels. And well, this is a study done by Jockware and their colleagues. And the interesting part is that for each of they have several configurations varying the spacing of the dowels, the size of the timber, but the interesting part is that for each of these configurations, they repeat in the experiment multiple times. So they allow us to capture somehow the statistical nature of the resistance of these connections. And well, here are more data about it, but they went from 7 tests up to 13 tests. So, and they capture both the mean and the coefficient of variation. So this gives us valuable information to characterize the distribution. And our goal here is to use this data to compare the Eurocode resistance versus a reliability-based interpretation of the experiments of this paper. So to see if we can do better than the Eurocode resistance. The procedure is the following. So on one hand, we use the Eurocode 5 formulas to calculate the design resistance of this connection. We transform the experimental mean and coefficient of variation to log scale parameters because we consider this resistance as a log normal random variable. We use Bayesian inference and experimental data to obtain zero predicted distribution. In this case, it's a conjugate prior case, so we can easily do Bayesian inference. And we follow the approach by the Eurocode. So in the background document of the Eurocode, they specify how one sets design resistance. And it's associated with a certain reliability index and a certain influence factor. So we apply this approach, but we use the resistance that we have obtained from our experimental results. And the idea is that if the ratio between the empirical resistance obtained in this way versus the one in the Eurocode is above 1, well, this means that the Eurocode formulas are more conservative than what they say or what that their target level says. And this is indeed the case. So for all the cases that I showed before, there is quite a big ratio, so quite above 1. So from 1.34 to 2.01, so it means from 34% higher to up to 100%. So yeah, this means that there is potential in using a reliability approach for this because it reveals these things that a simple code check might not show. So I hope that I have convince you why a reliability approach is useful for this task. So now we will move to going from buildings to populations. So information, well, this is in parallel to one of the previous slides that I showed. The information in buildings can be differently distributed and it's also sparse. So in one building, you can have maintenance records and visual inspections and material testing, but on others, maybe you only have access to the load history, but then nothing else. So we need a way to use this information so that we can complement what we know from one building to others, and we can draw interesting conclusions. So this goes by recognizing that buildings are not unique prototypes. So even though they can look different, they can share structural typologies, they can share material types, loading environments, and so on. So the population of structurally similar buildings can be much richer informationally than individually. So the idea would be to mathematically transfer what we learned from this sparse building data to the entire population. Of course, buildings are very heterogeneous, so this is not a trivial problem. We will have to tackle this. And yeah, here on the right is a picture of the skyline of Rotterdam. And you can see indeed that buildings are very heterogeneous. These are all very, very different. The Dutch architecture is very capricious on that regard, especially in Rotterdam. So yeah, this is quite a challenge that we'll have to tackle. So about this PhD project, the goal is in a few words, to develop a framework for population level reliability assessment. So the idea is to integrate mechanical modeling, Bayesian inference, and information transfer across media. So this is what we want to do after this long introduction. And I'm an external PhD. I'm matriculated here at the PH. I'm employed by TNL still. I'll be alternating between Delft and Zurich, and my supervisor was Eleni, of course, but also Professor Raphael Steinberg. He's my colleague at TNO. He will be my company supervisor, but also he's in University in Belgium. An interesting thing about this project is that we'll also focus on timber buildings. So this PhD is partially funded by the timber department, my company. And as I show in this small example, the preliminary research that we've done on timber also has found some evidence of timber capacity that can be reviewed with reliability approaches. So this is also partially where it comes from, where this comes from. So the idea is that not necessarily that we produce methodologies that are unique for timber buildings, but we want to use timber buildings as case studies. And we have partners in the Dutch timber sector that can help us with this. Okay, so now I will start talking about some challenges that we have identified so far, some preliminary work about them, and some ideas. So here we have two different structures. On the left, we have a simple truss. It's statically determinate, so meaning that the failure of any of the truss elements means the failure of a system. So you can calculate the reliability of each of these components, and then you can calculate the reliability of the entire system, and the second will be smaller than the first, because this is akin to a series system. So the safety of the system is lower than the safety of its components, because the failure of any component means the failure of the system. And on the right side, we have a different structure. Here we have some redundancy because the structure is fixed in both sides. So for it to fail, you need to form a plastic hinge on the left, a plastic hinge on the right, and then a plastic hinge in the middle. So if you consider each of these cross sections a component, then the probability of failure of a system is smaller than the probability of failure of those components. This is closer to a parallel system, not exactly, but closer. So component level reliability is not enough. So we need to study buildings from a system reliability approach. And this is unfortunately a hard problem because it involves high dimensionality. Buildings can be very large. They can have many members. They can have many failure modes, which means that we have a large number of random variables involved. Even more if you, for example, discretize your elements into several cross sections. On top of that, we have this has been here all the time. We have also complex correlations. So we know that loads are correlated spatially, but also temporally. Material properties also have spatial correlation. They have degradation. They have batch correlations as well. And it's not always obvious how to model. There's a lot of engineering judgment into defining them. There is some work by the JCSS probabilistic model code, but still it is not a closed matter. And finally, we also have a large computational cost. So we can have expensive analysis, which can be nonlinear, which can be time dependent, or maybe a combination of both. And as you know, reliability analysis requires many evaluation of the same structures with different realization of parameters. So put things in a concrete way, we have this example that we saw before. This is a 10-story reinforced concrete frame. The geometry is shown on the left. So here is a very regular structure, and we only consider gravity loads. So self-weight, permanent loads, and imposed loads, so light loads. And we consider per beam 3 cross sections. So in both sides and the middle, and per column, two sections. So one at the top and one at the bottom of each column. So this gave us a total of 270 cross section. And we designed the cross sections of this concrete frame so that the unity check under the Eurocode is close to 1. So we designed the dimensions of the cross sections and the rebar so that it's close to 1. This ended up giving us 671 correlated random variables. I will not go into more details about how the correlation structure is considered, but they are correlated. And some results about this. The probability or the reliability associated to any cross-section yielding here, it's 3.49. And the reliability associated to the most critical cross-section, so in isolation, it's a bit higher, of course. It's closer to 4.07. So not so since we designed this building to follow the Eurocode, the target in this case was 3.8. So the Eurocode target was 3.8. So it's not that far from that value. And we did it in a Monte Carlo way. So we did a Monte Carlo simulation with a large number of samples. And this is possible because these two evaluations are possible to do with linear elastic analysis. So this ends up being just a large matrix that you can easily parallelize and you can get results quite easily, even if you do it for millions of samples. And then we also study what happens in the nonlinear case. So we perform a plastic analysis. And for this case, of course, you cannot afford to do millions of simulations. It's much more expensive. So we used an approximated method. We use a method, subset simulation, that allows you to do it with only a few thousand evaluations. And of course, as you can expect, the mechanism associated with it has the reliability of mechanisms have a higher value than the others. So because the plasticity gives us some redundancy that we can make use of. So these are the results that we obtained. So from this, it should be clear that it is not enough to analyze only the critical cross sections or just check which is if any cross section yields, but we need to see buildings in a global perspective as well to be able to say some interesting things about it. Some ideas to go towards efficient system reliability. So we already, in this case, solved it with the subset simulation, but an interesting approach, and that is quite easy to implement actually, is to do a sort of two-stage Monte Carlo simulation. The idea is to use cheap linear elastic analysis to filter the safe realization. And then only on those that are not filtered, well, you run the expensive nonlinear analysis on that tail. So for instance, you start with 10 million samples, and then the check associated with any cross-section yield, which was 3.49. This is only a tiny probability of that occurring, so 0.024%. So this means that from those 10 million samples, only 24,000 samples demand a nonlinear analysis. And then for those, well, checking this reliability index, you end up having only 100 samples that have a plastic mechanism form. So this is a simple approach that can be taken if the typology of structure allows you to run this cheap linear elastic analysis. For instance, if you don't have any buckling phenomena, then you can easily do this and it can be efficient. Then going to perhaps more interesting approaches is to use a high dimensional model. High dimensional because we need to tackle with hundreds, if not thousands, of random variables. One idea is to do dimensionality reduction first, and then to use a machine learning surrogate, so some sort of PCA, and then complement it with Gaussian processes or something like that. But maybe, but another way of seeing the problem is to, for instance, use a graph-based surrogate, and in this way, you can also encode the topology of your structure. So you can train one network that is able to make predictions for different configurations of structures. And as I show in my example before, yeah, buildings are quite keen to be represented by graphs. So a joint can be a node, an element can be an edge, and then you can find a way also to deal with two-dimensional elements such as slabs, polygons. So this is also another approach that could be taken. Of course, we have not actually work on implementing any of these, but this is some ideas that we have at the beginning usually. So now another component of the PhD was the Bayesian approach that needs to be taken. And for this, well, the biggest issue, some of you that are familiar with Bayesian inference may know, is its computational cost. So from left to right on the efficiency of each of these approaches, Markov chain Monte Carlo is, of course, the gold standard in terms of accuracy. In terms of if you let it run long enough, you'll get the right posterior distribution, especially with the modern methods such as Hamiltonian Monte Carlo and so on. So this is the gold standard, but it's expensive for building, and it's also sequential in nature. So one way that researchers have tackled this is with the use of variational inference, very popular in the machine learning literature. It's approximate, but it's faster. And this frames the problem not in terms of sampling at an MCMC, but in terms of optimization. So you optimize the parameters so that you are similar to the posterior that you are looking to obtain. But still, it's data set dependent. So there is a third you can say paradigm on Bayesian inference, which is amortized inference. So the idea here, borrowing again from machine learning and specifically from normalizing flows, you train once and then you can obtain fast inference for new observations that you have. So you train once with the simulations with the data generating process that you have, and you can obtain instantaneous inference. And it's Bayesian inference. So if your network is perfectly trained, then you do get the posterior. Of course, you never get that. You get approximations, but it's still quite useful for many tasks. So amortized inference in particular looks very promising for population tasks because of this efficiency that I mentioned. And this is a picture of one of the frameworks of Bayesian inference that are more popular nowadays, Bayesflow. And then, well, I will not go into much detail about how this framework works, but you have a training phase that is run in a forward manner. So you have a prior distribution, you sample some parameter values, then you pass them through your simulator, you generate the simulated data, and then you pass them to what's called a summary network. A summary network that does what in Bayesian inference is known as producing summary statistics. It is a way of doing some dimensionality reduction. And then these summary statistics are the thing that your network is conditioned on so that it can give you the samples of your posterior distribution. So it's trained in a forward manner, and then for the inference, you switch the button into the second network, which is the invertible neural network or conditionally invertible neural network. And then, yeah, you can, by sampling from a normal distribution, you pass them to your network, condition on your observation, and you get samples of the posterior distribution. And it's quite interesting because you do obtain the samples from the backward mode of running this network. And then if you want to calculate the densities, you can also do that in the forward mode. So you have access to both, which is sometimes useful. So this is a likelihood-free method. The summary statistics are not handcrafted but learned. This is important because in approximate, what happened? Yes. In approximated Bayesian inference, usually you have to define what is an important summary statistic, and this may contain some biases, and it will never be as optimal as statistics that are learned from the data. So this is trained only on simulations. It performs fast inference for any arbitrary data set, and it's suitable for any data type that can be modeled with neural networks. This is also quite interesting because if you have data that is sequential in nature, you can use a recurrent neural network. If you have data that is grid-like, you can use a convolutional neural network. If you have data that is arranged as a graph, you can use a graph neural network and so on. So The summary network allows you to take into account these different shapes of the data that you have. Put some interesting biases that you might want to introduce. And we have experimented with amortized inference in the past. Here we have an example. Here's a small scale bridge that we have at TNO. It's a 1.5 meter structure. It's a truss structure, as you can see. We have a little car that goes from left to right, and then we also have some sensors there, and we can obtain the influence lines of this little card for each of the sensors that we have. And the interesting thing about this bridge also is that damage can be simulated. So we have some pieces that are identical to these blue ones that you're seeing there, but they have a smaller Young modulus, and in that way we can simulate damage if damage can be interpreted as a reduction of the Young modulus. So we use this as a case study for model-based damage detection via amortized inference. We started with that work, and then we had a master thesis intern that on top of what we have developed in the past, he added a graph-based summary network, the thing that I presented before, using the joints or representing the joints of these truss structures nodes and the bars as edges. And what we saw is that there was a strong performance across multiple damage cases. So using the graph structure gave us better results than not using them. And even an interesting approach also could be to amortize over the topology as well, because this is possible in amortized inference. You can amortize over the number of samples, over the number of observations that you will have, over the locations of sensors that you may need, and in this case, over even the topology of the structure that you're considering. And finally, moving to the third part of the last challenge that I will be talking today is how to share information across building structures. So for this, we have two previous studies at TNO. One from a colleague, the one on the left, focuses on the reliability of slab floors using a population track record. Track record means the fact that it has survived for many years with operational loads. And well, this study was done because in the Netherlands we suddenly had a catastrophic failure of some concrete slabs that were very used in parking lot buildings. So structural failures of the collapse of the actual structure, and there was a necessity of evaluating if there need to be a massive retrofit campaign in thousands of buildings. But using this population track record concept, then they were able to only minimize the actual retrofits that needed to be done. So the populations here were determined manually by the analysts. By engineering judgment, they say, okay, these floor slabs, well, I'm going to group them in one population, and then, for instance, if you have a different thickness, well, this will go to another population. So it works completely separated, and well, that worked fine for that application. On the right, we have reliability of facade attachments. So these are used for the cables that sustain the public lighting in Amsterdam. This is a consultancy that we made for the municipality of Amsterdam, because they do proof loading of these facade attachments. So that means that whenever they want to put a heavier light, in this case, they were switching to LED lights. So the LED lights are heavier than the original ones. They needed to proof load to determine if the structure was fit for purpose. Because, these attachments may have more than 50 years. They don't have any documentation or sparse documentation. So the way that they ensure that this was fulfilling its specifications was by applying proof loading. And they came to us and asked us if they could do better, if they could reduce the proof load values that they were using, because they were starting to crack some facades, they were starting to have a lot of rejections, and they needed to do better. So what we did there is we took the actual data set that they had produced. It was censored in a way that, or partially censored, because it contained both failure and passing samples. So a failure, then you have an actual measure of resistance of the anchor, but if it's passing, you only have an access to a lower bound of it. So, and actually, this enables us to use survival analysis, which is a really rich field of statistics, and we use it for this purpose. And the way that we treated these different anchors that were in different facades, and they were different configurations, and they have had historically different loads. Well, we treated as a single population, and the heterogeneity here was handled by modeling as covariates in our statistical model. So the thing is that the composition of populations might not always be as simple as in these two cases that I have described before. So we need to construct the population in a more sophisticated way for heterogeneous buildings. So some ideas here for handling more complex population structures. One way of doing it is by hierarchical Bayesian modeling. So this is very powerful if you know the full data generated process. If you have a lot of knowledge about the thing that you're describing, then you can use hierarchical Bayesian models. Another approach, more from the machine learning perspective, is to somehow measure the similarity between these two buildings that are being analyzed, and then apply some transfer learning. And finally, perhaps a hierarchy of can be automatically learned from the data if you have enough. So somehow maybe you can learn that hierarchy. But I talk about the data because for this project we will have access to quite a rich data set of vibration-based monitoring data for Dutch high-rise buildings. So this belongs to a consortium. It's not directly related to this PhD, but we will get access to the data. So we have on the top long-term campaigns that have been done in these buildings with accelerometers. They have extracted frequencies and mode shapes, and also short-term monitoring data that maybe spans 1 or 2 days. So this is very interesting because all of these buildings are very different. The data that you obtain in each building is different, but yeah, we think that it can be of great use for a population level approach. And yeah, so one interesting thing that we'll probably discuss with Eleni and Rafael afterwards is yeah, what research sequence to follow in this PhD. Because on one hand, we can do a bottom-up approach and first study well what reliability means for timber buildings, then move on to Bayesian updating, and then move on to a population level approach. So this is let's say a logical way of approaching it, because each stage produces the tools and intuitions that you may need. You learn what matters mechanically before moving to the next stage, but you can also do it in the other way around. So you can always start from a population level approach, and you can discover early so how precise or how detailed your models need to be so that you can draw interesting population level conclusions. So it's possible that some coarse models may suffice if you pull across a large number of structures. This is a question for the audience more. So we have not made a decision of how to proceed, but yeah, I just wanted to leave it there. Yeah, just finalize the presentation. We discussed why following a reliability approach. In summary, because it eliminates the false certainty of pass and fail unit checks. It provides an actionable metric, for instance, allowing risk-based optimization, and it integrates new information via Bayesian inference, or it allows you to do that. The central thesis of this starting PhD project is that a population level framework can overcome the individual data sparsity, so you can share information between population fields. And finally, 3 challenges that we have. the complexity of system reliability of buildings, which can be very large on one hand, the computational burden of phasing and updating, or the degree of approximation that is required. And finally, the issue of information transfer across heterogeneous buildings. So yes, this was my presentation. Thanks a lot for your attention. And does anybody have some questions?